Alright, so here we're proving that if A is closed and X is not an A, then the distance between, you can set some number D such that the distance between X and any point in A is greater than or equal to D. So we're basically putting a bubble around A that will sort of, like, basically you can expand a little bit and still not touch X. And if you think about this, this sort of means that X is not on the boundary of A. And if you talk about basic topology, that makes sense because closed sets contain their limit points. But that's more when you actually study point set topology in a little more detail, which you can do either in Munkers or in a book like Baby Rudin, i.e. Principles of Mathematical Analysis. Alright, by the way, there is a name for spaces in which this fact holds. Is it are they... No, it's not Hausdorff. Separable? I don't know. It's one of those words. But anyways, so this is basically, these are all things that can be generalized. There's a lot of things that we're talking about in this section that you can generalize when talking about more general topological spaces. And so it's really interesting to go back and see these exercises, whereas here these exercises seem like, okay, that's an interesting topic, but then you sort of come back to them later on and you learn about more general classes of sets which share these properties. But anyways, let's go ahead and do this exercise. Alright. So, since A is closed, the complement of A is open. Let X be not in A. So because it's open, there exists an open set U. Let's call this, we'll say it looks like this, AI to BI, such that X is in U, and U is entirely contained in the complement of A. That's because A complement is open. So the fact that U is completely contained in the complement of A means that the intersection of U and A is empty. Now we're going to let D be the minimum over I between 1 and n of the minimum of xi minus ai and bi minus xi. So the reason that we're doing this is that we are the reason that we're doing this is because X is in U, and X could be close to the endpoints of, for each index I, X is somewhere in between AI and BI, and it could be really close to one of them. So we want to figure out which one it's closest to. And this will be useful later. So anyways, D, this is going to be the D that we choose. Let's see here. So we want to prove that this D does exactly what we claim that it does. So suppose Y satisfies Y minus X is greater than or equal to D. So we want to prove that there's a number D such that for any Y in A, this norm is greater than or equal to D. Oh, okay, so here's what we're doing. So what we're going to do, so we want to prove that if y is an a, then the norm of y minus x is greater than or equal to d. The contrapositive of that statement is that if it's not the case that the norm of y minus x is greater than or equal to d, then it is not the case that y is an a, i.e., if the distance between x and y is less than d, then y is not an a. So we're going to suppose that y satisfies this inequality. We want to prove that y is not an a. Assume for a contradiction that y is not in U. Then this means that there exists an I such that yi is not in the interval from ai to bi. Because if no such I existed, then each yi would be in the interval from ai to bi, which would mean that y would be in U. So, this tells us that the distance between xi and yi is greater than d, because yi is not in ai to bi. So the distance between yi and xi is going to be, let's see, it's going to be greater than both the distance between xi and ai and the distance between xi and bi. But both of these things are values which are greater than d, because d is the minimum over a set of things, including those two distances. And so this norm is greater than d. Okay, so thus, the norm of x minus y equals the sum from I equals 1 to n of xi minus yi squared. Now, here, taking a square root of a positive number is positive. Inside the square root, we're adding up a whole bunch of positive numbers. So if we throw out a bunch of them, then the sum will become smaller. So this is greater than or equal to, let's throw out every index other than this particular I that we've chosen. So I guess, here, let's call this, just to be clear, let's call this j. B, j, x, I, y, I. No, x, j, y, j, greater than d. So then this is greater than or equal to, we take xj minus yj squared, square root, because we threw out every index that isn't j. But then this is just the square root and the square cancel, so it's just the absolute value of xj minus yj, and so that is going to be greater than d. And d is greater than the norm of x minus y. So we've proven that the norm of x minus y is strictly less than itself, which is impossible. Thus, y is in U. By the way, I probably should mention at this point, proofs by contradiction are not ideal, because there's a lot of times, especially when you're starting with writing proofs, where you do a proof by contradiction and you end up with a proof that looks very similar to what the proof would be if you didn't use contradiction. So the point is, you only really want to use contradiction when you absolutely have to, because it's just good writing. Because there's a lot of times where you have proofs that could be done without contradiction, but you do them using contradiction, and the contradiction argument is messier and takes longer to write than the non-contradiction argument. So whenever this is the case, it's better writing to not use contradiction. And so, yeah, just as So the thing is here, I don't know if there's a good way. I mean, there could be an easy way to do this without contradiction that I'm just not seeing, but it's not really a big deal. Having a proof by contradiction is certainly better than not having a proof. But sometimes, if you want to make your argument the best it could be, it's ideal to try to find a proof that does not use contradiction. But sometimes it's necessary, and that's not a bad thing. Okay. So, if y satisfies norm of x minus y strictly less than d, then we get this contradiction. And thus, y is in U, and U does not intersect A, so y is in A complement. Or rather, y is not in A. Contrapositively, so we've proven that if the norm of y minus x is strictly less than d, then y is not in A. The contrapositive is that if y is in A, then the norm of y minus x must be greater than or equal to d. And that's what we wanted, as desired. By the way, it sort of makes sense here. This D is not, there's nothing special about this D. You can choose this D. We've chosen this particular D. D could be smaller and still work. In fact, if you just let D be, if you replace D with D over 2, then it will certainly work as well, because then the norm of y minus x will be greater than or equal to D, which is strictly greater than D over 2. Another thing to note here is that this D might not be optimal, because it's sort of interesting. When you look at this inequality where we went from a sum from xi minus yi squared to being greater than just the norm of xj minus yj, we threw out n minus 1 terms. So we threw out a lot of information. And so this is a very rough estimate. And so that sort of, I don't know, if you're thinking about estimates, I feel like a lot of times the most difficult estimates to prove are the ones where you can't throw out very much. You have to really work as well as possible with the things that you have, and be really efficient in your inequalities, and try to make your inequalities as sharp as possible. So here, it isn't necessary to have a really sharp estimate, but we also, and for that reason, we're able to throw out a whole bunch of information here and use a really rough estimate, but still, it works. Just a small thing to keep in mind, it might not be useful to you depending on what you study, but if you study something that involves like more advanced analysis or like lots of error estimates and things like this, then it could be good to keep in mind that whenever you're throwing out a lot of information, you should always think, is this necessary? Could I be doing better? Alright, so anyways, moving on to B. If A is closed and B is compact, and these sets do not intersect each other, prove that there is a set D such that basically this inequality holds, but for all points in A and B. And so this is basically just, instead of putting a bubble around A, we're putting bubbles around both A and B, and it works. By the way, in my notation here, they choose y in A and x in B. I'm going to do x in A and y in B because I like A comes before B in the alphabet and x comes before y in the alphabet. It's not a big deal, just I'm making it clear that I'm going to be using a sort of a notation that's inconsistent with the exercise. Okay, so for all y in B, we know by the proof of exercise A that there exists, well, not by the proof, but by the statement, there exists a d, and we'll call it dy, such that distance between x and y is greater than or equal to dy, and this will hold for all for all x, which is an a. And in the proof, if we let uy, and we'll just write this out into n, ai, bi, be a neighborhood of y not intersecting a, and we also defined dy to be the min for I between 1 and n of the minimum of yi minus ai and bi minus yi. Alright, so we want to use this same estimate. We're writing the dy's out, this dy out again because we're going to need to reference it, but it turns out this isn't enough. Or rather, it may be enough, but in the proof that I've come up with, it's not enough. So instead, we're going to need a smaller neighborhood. So we're going to let vy, this is going to be I equals 1 to n, and we're going to take yi minus, and we're going to take dy divided by 2 square root of n, and then yi plus dy over 2 square root of n. So in each index, we're decreasing the radius by a factor of 2 square root of n on each side. Then y is in vy, and vy is contained in uy, which is contained in a complement. So in particular, vy intersected with a is empty. Alright. So now vy, if we take all vy's as y ranges over c, that's, what? No. Y is in b. I call it C because it's compact. Right? B is compact. B is the compact one. Okay, cool. Alright, let's scroll down a little bit. So this is an open cover of B. So, by compactness, there is a finite subcover. And we'll call this Vy1 through Vym. Now we're going to let D be a positive number which is less than 1/2 times the minimum over all j between 1 and m of dyj. Okay, so let's see here. Oh, I don't know if my proof works anymore. Let me think about it, because what I say here is now choose any x in A and y in B. And that can't work because we've already fixed x. Rather, we should say we need to choose this x that we've chosen already, that's fixed. So now choose any, we'll call it, no, we're using a's as indices. Z in A and any y in B. So of course now we're completely throwing out the window the whole alphabetical order thing, but whatever. Okay, let's see if this argument still works. Then there exists a j such that y is in Vyj, because the Vyj's are a cover of B. So then we do an estimate. Alright, and so I'm going to have to do this estimate on the fly because we're doing the distance between z and y, and we end up using the reverse triangle inequality. So this is going to be the distance between, okay, so there's another term in here, so z minus x plus x minus yj plus yj minus y. No. Yes. Let's do this step by step, just to make it clear. So it's going to be greater than or equal to this minus this. And of course we can remove the absolute value signs. Well, wait, if this is supposed to hold for any z and a, we're not going to get any sort of bounds on the distance. But wait, does this matter? We want this to be greater than dy. I'm not sure if this argument is going to work. Oh, wait a minute, what am I talking about? We didn't fix x. There exists a dy such that this norm is greater than equal to dy for all x and y. So we haven't fixed an x. Okay, so that's why this argument works. Yeah, I'm sorry about that. Okay, so after that hiccup, here we go. Then, the norm of x minus y is greater than or equal to distance between x minus yj minus yj minus y. This is just a reverse triangle inequality. And then we can remove the absolute value because the thing could only possibly be, that could only affect the sign, and so the sign could only possibly make it negative, which would actually be good for the inequality to hold, because you'd have a positive on the left and a negative on the right. Alright, and so then this is, so the distance between x and yj, well, x is an a. We know that, so there is a neighborhood, so the distance between x and yj is going to be greater than dy. No, it's, the distance between x and yj is going to be greater than or equal to dyj by the definition of dyj. dyj was chosen for this particular reason. Okay, so that's going to be a greater than or equal to, but we're going to get a strictly greater than for the next part. So if we look at yj minus y, well, yj is in Vyj. And Vyj, each index has a radius, or each Vyj goes from minus dy over 2 root of n to yi plus dy over 2 root of n. So for each index, the distance from the distance from the ith index of y to the ith index of yj has to be strictly less than the radius. And because we're subtracting it, it becomes greater than. So here we take the norm, and it's going to be the sum from I equals 1 to n, and on the inside we've got dyj over 2 square root of n. This entire thing is squared. Then we have a 1/2 on the outside. Okay, so then this is equal to, so we've got dyj minus, and then we've got, let's see here, if we sum this thing up, we've got n copies of the same thing, so it's just n times, and then we just square this thing. So n times dyj squared, and we're dividing by 4n, and taking the square root. And so this is equal to dyj minus, and then the n's will cancel, and then we end up with dyj over 2, and this equals 1, or this is just dyj over 2. And we chose d to be less than 1/2 the minimum of the dyj's. So in particular, d will be less than this particular dyj. So this is greater than dy. So for any x in a and y in b, the distance between x and y is strictly greater than dy. This holds for all x in a and y in b as desired. That's what we wanted. We wanted this thing to hold for every single x in a and y in b. And so that's that. Did I forget to do part C? Give a counter. I did. Give a counterexample in R2 if A and B are closed, but neither is compact. Okay, here's what I'm thinking for this. We want two sets that look sort of like this. So let's call this A, and we'll call this B. And what's going to happen is that these sets get closer and closer and closer. They never touch, but they get closer and closer and closer. So that their distance, so that there is no number such that their distance will be always greater than or something. So let's think about this and see if we can if I can come up with something on the fly. So let's think. So I'm thinking sine waves here. So let's see here. If we've got a sine wave here, then what we want is we want something that goes like this. All right. So let's see here. So this could be, so to begin with, we can have y equals sine of x and y equals minus sine of x. But this one will add something to it. So if we wanted them to exactly touch, then we would have something like this. And so what would this be? So this would start at 0, 2. If I'm just graphing this. Right, because 0 will go from -1 to 1, and 2 will go from 1 to 2. So this is going to be sine of x plus 2, and this will be minus sine of x. But we don't want these to, so if we just do these, like the first phase of these will actually precisely touch. And we don't want them to exactly touch. So we want this phase to be slightly less than. So we want we want to reduce the amplitudes of these by a little bit, but then the reduction of that amplitude, we want that to decrease as x goes to infinity. So instead we want these things times, okay, so we want something which starts as a positive number and then increases to infinity. Starts as a positive number between 0 and 1, and then increases to 1 as x goes to infinity. So maybe x over 1 plus x. Or something like this. Let's think about this. Not 1 plus 1. Come on. Okay. So yeah, as x, so this will always be less than 1 because the denominator is bigger. No. We need the plus 2 out there, so this is going to be, okay, so here we go. Let y1 of x be x over 1 plus x times sine of x plus 2, and we're going to let y2 of x be minus x over 1 plus x sine of x. Alright, so we want these to be closed sets. That do not intersect. And that is the case, or rather, let A be the set of all points x and y1 of x, where of course x is in R, and B is going to be the set of all points x, y2 of x. So to prove that they don't intersect, for every x, the y-coordinate of, or for every x, y1, no, let's have y1 be the smaller one. So this will be y2. Wait, the one on top should be the, no, this works. So y1 should be the smaller one, and y2 should be the bigger one. Okay, so for every x, it should be the case that the y value of y1 of x should be less than y2 of x. So y1 of x equals negative. Well, let's say this, the norm of y1 of x equals the norm of x over 1 plus x sine of x. And so this is going to be less than or equal to the norm of x over 1 plus x, and the sine of x is going to be in absolute value less than 1, and so that's fine. And so then this, if we take the norm of y2, we're going to get the norm of x plus 1 over the norm of x over 1 plus x plus 2. So let's see here. So this is precisely because you know what, let's make this greater than or equal to 0. How am I going to prove these are closed? Oh well, let's get to that later. this is, so because x is greater than or equal to 0, this is just this. And this is going to be less than or equal to, well, this is going to be strictly less than x over 1 plus x plus 2. Which is precisely norm of x over 1 plus x plus 2. Wait a minute. No, this isn't going to work. Let's start this way. Minus x over 1 plus x sine of x. No. This is the other one. By the reverse triangle inequality, this is greater than 2 minus this. This is precisely 2 minus this. Because sine of x is less than or equal to 1, this is going to be greater than or equal to 1 when we have the subtract, so it's 2 minus norm of x over 1 plus x. Oh wait, but this, the norm of this thing is going to be less than 1. So if we subtract this, this is going to be greater than 2 minus 1, which is 1. And here, this is less than 1. So there we go. y2 is going to be, y1 is going to be strictly less than y2. So y1 well, the norm of y1 is going to be strictly less than the norm of y2. So why is this useful? Because what we want to prove is that y1 is not equal to y2. Well, if their norms aren't the same, then they're certainly not the same number. So y1 is not equal to y2. There might have been a clearer way to do that. Oh well, I'm doing this on the fly. How do I prove they're closed using the facts that we have? Using the facts that we have, I mean, it's sort of clear visually, because you could just take a point that's not in the graph and put a box around it and you're good to go. Beyond that, I don't have a good way to prove this. So that's not good. If we knew more about general topology, I could use a fact about limit points. Closed sets are sets which contain all of their limit points, and so you can prove without too much difficulty that because A and B are graphs of continuous functions, they contain all their limit points. These are continuous and, continuous functions. Okay, so I'm just going to say A and B are closed, and sort of leave it to you if you want to go into more detail about why they're closed. I don't know how you'd go about finding the radius of such a box to guarantee that doesn't intersect with any of these graphs, because you might have to do calculations and it would be difficult. But in any case, I'm just going to say they're closed. So now we need to prove that they get closer and closer. So let's see here. They're going to meet at let's see here, 3 pi over 2. y1 of n times 3 pi over 2. Well, n is the dimension, so... No, it's 3 pi over 2 plus 2 pi times some integer m. This is going to be, well, if you take sine of 3 pi over 2, you're going to get minus 1, and so that's going to cancel. And so you're going to get positive 1. So you're just going to get 3 pi over 2 plus 2 pi m over 1 plus 3 pi over 2 plus 2 pi m. And y2 of, let's see here, y2 3 pi over 2 plus 2 pi m equals, so now we're going to get sine of x, so it's going to be minus 3 pi over 2 plus 2 pi m over 1 plus 3 pi over 2 plus 2 pi m. So it's going to be 2 minus this. So we know already that y1, the absolute value of y1 is going to be less than or equal to y2. Why do we even need the absolute values? y1 is going to be this thing, but it's going to be less than or equal to the absolute value of it, trivially. And then we don't even really need the absolute values here. Because this is greater than, because this thing is going to be greater than 1? You should be able to just have this, right? Because norm of this is greater than that. Because, let's see here. So the sine of x times x over 1 plus x, that's going to be greater than minus 1. Because sine is going to be greater than or equal to minus 1, and the scalar makes it that. Okay, so yeah. So here we go. This is a little nicer. Okay, so we know that y1 is strictly less than y2. But this, if we take the limit as m goes to infinity, this is going to go to 1 as m goes to infinity. And this well, wait, what we really need to do is take y2 of that minus y1 of that. When I just put this dot, I mean to write 3 pi over 2 plus 2 pi m, but I don't feel like writing that out again. So this is going to be minus 2 times this fraction, this 3 pi over 2 plus 2 pi m over 1 plus blah, 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 blah. By the way, this is why the division symbol looks like that, because you're just taking something divided by something, and the somethings you're denoting by dots. So this is 2 times 1 minus, and then we got this, I'll write it out again here. 3 pi over 2 plus 2 pi m for 1 plus 3 pi over 2 plus 2 pi m. And as m goes to infinity, this term over here will go to 1, so this will go to 1 minus 1 is 0. 0 as m goes to infinity. So for any d greater than 0, there exists x in A and y in B such that the distance between x and y is less than d. Because you choose m large enough so that this 2 times 1 minus whatever is less than d, and you use that. And so there you go, we have a counterexample in R2. Okay, so sorry, I didn't come up with the example for this beforehand, and I don't know how to prove that this is closed, but these sets A and B will work. They're closed sets, they get closer and closer, but they never touch. And so it's a counterexample to the exercise, or to it answers the question that was in the problem, and so we are done.